Here we're going to use something called a factor tree. What we're basically going to do is split the number 24 into what's called its prime product factorization, PPF, or just the product of its primes. What we're going to do is try and split the number 24 up any way we can by multiplying. So think of any two numbers that multiply to give 24. I'm just going to go for 3 and 8. And I keep splitting these numbers until I can't split them any further. The number 3, you think the only way to split that is 1 times 3. Well, it's a bit pointless doing that, because then I could keep going and going and the tree would never end. So that doesn't make it any simpler. That means I can't break the number 3 down. It's unbreakable, and that's another way of saying that it's a prime number. So I can't go any further on that side of the tree. I now get the number 8. Well, that's 2 4s. Now I can't break the number 2 down, because that would be 2 times 1. I'm just repeating myself, so there's another prime number. The number 4 I can break as 2 times 2. Again, I've got prime numbers. So what we then do is write it down as its prime products, and write them from smallest to largest. 2 times 2 times another 2 times 3. And finally we should really group these 2's together. We could write that as 2 to the power 3, because there's 1, 2, 3 times we're multiplying, times by 3. And this is the prime product factorization of 24. Now I could just continue that idea with a second one. So if I take something like the number 18, again break it down. Two numbers that multiply to give 18. You can break them in any way you like, the end will always be the same. So I'm going to do 2 times 9. 2 is a prime number, can't be broken down. 9, that breaks down into 3 times 3. 3 can't be broken down, neither can this 3, giving us prime product factorization of 2 times 3 times 3, which is 2 times 3 squared. And there we have it. A good use of factor trees is that you can actually use factor trees to find HCFs and LCMs. If you watch, take the number 24. We've seen that we can split this up into 2 times 6, 2 times 3 for my factor tree. If I do the same with 18, I get 2 times 9, which splits into 3 times 3. Why are these useful? Well, if I want to find the HCF, all I have to do is find a prime number that's in both trees. So here's a prime number 2, that's in both trees. Now you may say, well, there's 2 2's here, but that's not one in each tree, so I can't use them anymore. So there's no other 2's, but I can take a 3 from both tree. There's nothing else that's a pair anymore. So I've now got the highest common factor is 2 times 3 is 6. If you want to take that one step further, the LCM is this number here times by whatever is left over. Now what's left over is another 2, another 2, and a 3. So that's 6 times 2 is 12, times 2 is 24, times 3 is 72. There's a use of a factor tree. I'm not going to tell you why that works, that's just a little mystery for you. Okay, I'm going to find the HCF and LCM of 35 and 25. First, split them into their factor trees. That's 5 7s are 35, both prime numbers. 25, that one just splits to 5 times 5. So the HCF, find anything that's in both trees. There's a 5 here and a 5 there, giving 5, nothing else to share. The LCM is your answer to the HCF, which is 5, times by the leftover parts. Well, there's a 7 here and a 5 there. Now that gives me 7 lots of 25, which is 175.